everybody for being here. I'm very glad to participate to this conference. Okay, my name is Matteo Sacchet. I'm from Italy. I'm the name in boldface. And this talk of today will be about the creation of animated graphs to develop STEM, computational thinking in support STEM education. Okay, just to say a few words about say the background, because I am from Italy, so it's say quite far away from here. So and it's very useful to know the background just in order to understand better what we did say in all this presentation of the paper. Okay, in this case, say Turin is a city in the northwest of the country. Okay, it's one of the biggest cities in Italy, probably the fourth one or something like that. And it's surrounded by mountains, and it was a former capital city of Italy. I want just to stress a little bit that it's surrounded by mountains because we apply also, say, digital technologies in order to reach, say, a wide range of the population, because, say, some of them are in valleys, so very difficult to reach in other ways. And university in Turin is quite ancient, so it was from the 15th century, sorry. And there are thousands of students attending all the courses. We have plenty of course study, except from engineering and architecture, since there is another university in Turin, because so we are skipping all the engineering stuff, but still we have plenty of mathematics in all our courses. Well, this one, it's the Department of Mathematics where I'm working, actually. And okay, so this is the group. Okay, there is more people in the research group than the one stated in the authors of the paper, because we are a group working on digital education, in say quite general digital education, mainly in mathematics. So because this group was born at the Department of Mathematics, so it's mainly composed by mathematicians. So most of these people are mathematicians, but we need also other areas of expertise, because we have also some computer science experts and linguistic experts in order to make, say, our work more international. And about the using of Maple at the university. Okay, we started, say, really since the beginning of, say, the dawn of the software, say, mainly for research in the 80s. Then, say, some professors started using it at the early, say, the beginning of the new millennium for education, with university students. And now, say, more or less 20 years after, we are using it for many projects, projects for secondary education and projects for tertiary education. Most of the projects, of course, are about STEM disciplines, but not only, actually. Okay, here is just a little list of all the projects we are managing as group. The one on the left part of the screen are for mathematics or STEM disciplines in general. So and these projects are related both to many target people. Let's say the first one, this one is for teachers, for example. The other one, okay, this one too. This is in two different settings. The PPS project is in a national setting. The SMART project it's in a European setting. The other one are devoted to students, this one here, to recover gaps, to, let's say, help very good students in order to be really the best. But we use really the Maple system, let's say, with all these tools. Even in other projects, like involving even languages or physics, or even for university guidance, and yeah, really general projects. And okay. Oops, okay. Okay, so now let's go directly to the work that we did in this paper. Okay, we are first dealing with, let's say, computational thinking, because we try to develop computational skills in students and not only, as I said. So we just made an overview of what really does it mean to develop computational thinking skills. There was a paper, my Jeanette Wing, which states, okay, that there is no actual definition for computational thinking, but there are some features that Jeanette Wing stated. Say, for example, is something that it's typical for human, not for a machine, or it's a base for conceptualizing. So it's really based on a different level of abstraction. It's made basically for ideas. Its foundation, it's in mathematics, but it's typical also of engineer and computer science. And it's a process that it's open really to everyone all over the world. So maybe for students, teachers, and all the people involved in the education system. Other authors stated the features of computational thinking. And in this work, we focus more on the mental strategies because okay, there are also other features, of course. There are some transversal competencies related to computational thinking, some methods, some practices. But the mental strategies are the one which we which we started focusing on. And the authors, the one in this one, Lodi et al. Stated some of the mental strategies that are behind, say, computational thinking. For example, there is algorithmic thinking. Okay, for a student, let's say, make a sequence of steps in order to get to a solution, for example. There is logical thinking, to establish and control facts. There is also the strategies of decomposition. So you have a really complex problem. You divide it into into sub-problems. There is the strategies of abstraction. You have a contextualized problem, which we use a lot, the contextualization for maths, like the seal of the previous talk. And so students need to, let's say, focus on the relevant aspects of the problem. There is also the strategy of pattern recognition. So find regularities and recurrences. And also the generalization. Okay, I have done some calculation, create a model in a specific setting. Now I want to generalize and to see how it works, maybe changing parameters, changing the fertility of seals, and stuff like that. And so since our projects are, and computational thinking, both of them are strongly related to mathematics, we focus on this because we apply some problem-solving strategies. Okay, problem-solving, what does it mean? It means many things, but for students, they need to understand the problem. They create a mathematical model. They solve this model. They infer something from it, and they give an interpretation of what they get. But we want to really shift a little bit the strategy in order to we apply this computational thinking in order to make students solve problems. In during all the projects, we give students problems which are divided into steps usually. The last step usually is a kind of generalization. I want you to really change something in the setting in order to see how the model works in different situations. And this is very nice with the use of Maple, which we usually call the advanced computing environment, because really the computational tools are very powerful. And students need also to write down algorithm or something, or text or images in an appropriate language, and in order to let other user, other machine, other things really understand and really have a direct impression of what was the problem, how the student solved it. Okay. okay, you know more or less all of you the potentialities of an advanced computing environment, and students uses more or less all of them. Okay, from really the text. Okay, we ask students to write a lot of comments in what they're doing in order to be when you solve a problem, so you need another people really understand better what is seeing, and also the numerical computation, symbolic computation, and programming language, and all this, which is everything is very good for mathematics teaching. And in this work, we focus a little bit more on the animated graphs. Okay, not all the problems are suitable for animation, but we focus on just one problem, which was very good for this setting. Okay, there was a little bit of dynamic, but of course, really, we applied also Maple, for example, for logistic problem or stuff like that. And okay, we use a lot of animation. Let's say, for example, really, we start training students with really basic example. For example, yeah, I have a parabola. I want just to see how does it change when I change the main parameter, the coefficient of x squared. So we just train students how to really generate an animation. Okay, you need a parameter for the animation and an interval in which this parameter varies. Okay, and in this setting, what are the processes of computational thinking that are involved while creating or developing, solving a problem, and finally getting an animation? Okay, the contextualized problem that we focused on is this one. We have a ladybug, which is on this part of a wheel of a bicycle, let's say. And the ladybug stays there because it's a very stable insect. And we ask the students to find the trajectory of the ladybug in 1 kilometer. Students, of course, this one is quite suitable for animation. We analyzed 16 solutions made by students. Students were something like grade 12, or similar kind. And okay, we had got, even if the problem was like fixed, okay, and the solution is just one, let's say, but from the student's perspective, we had really different strategies, different processes that were activated. So, for example, some of them, say, create an animation like making a curve appearing point by point. Some of them made an animation in order to verify the results. I will explain something in detail later. Some students made like union of animation, and some students may prepare a procedure, so a lot more computational. Okay, and I also say something about some incorrect procedures in which the computational strategies, the mental strategies, were, let's say, not correctly adopted. Okay, so the first one, for example, is an animation where students create a curve like point by point. Okay, you see, I don't see in my screen, but you see it here. Okay, the students, was just really the simple command that the student applied. Okay, this was not the real, the whole problem. There were many steps in between and further things, but we just focus on the animation part. And students, in this case, they applied the strategy of decomposition of problem, because here you see that students wrote down the rotational part of the motion and the translational part of the motion, because so he divided really the motion into two into two sub-motion, let's say. So he decomposed the problem. And then he made also an abstraction in order to join them into a single graphic. Anyway, in this case, it was still a wrong solution, because we always remember that the solution is contextualized in the setting of the problem. So in fact, the ladybug was starting from from the bottom of the wheel. So probably the students didn't get all the points, but still he applied some correct strategies, even if not all of them. Okay, some students also try to verify their results. So what did they do? This is really, again, the simple code that the students wrote. In this code, there are really two main parts. There is this, the ladybug, which is moving so just alone in somewhere. And there is, behind it, there is the static graph of the motion. So this, the student make an abstraction in order to create both the static and the animation. But he applied also a little bit of logical thinking, because he wanted to check the correctness of his solution. Because you see in the code here that here is the motion of this point of the ladybug, but he wrote down also a background in order to, let's say, see if the ladybug was moving correctly in this motion. Okay, some students have also made some pieces of animation and then join them all together, like this one. In this animation, for example, you see there is the point which leaves a trace, of course. There's the center, there's the radius, so there are two pieces of circle in there. So there are, say, 5 different objects, let's say, in this animation. And so students decompose solving the problem, say, creating this animation into 5 sub-problems. But then, while joining all together, you had also to adapt the time, the timing of the animation and all of it. So you have to understand all the patterns that were involved in all this single animation that were joined together. So here is the code. There you see. You can see actually, say, very directly from this code that it's the composition of problem, because there are these 5 different animation. Okay, and the student also adapted very well the timing of the animation with all these parameters which are in between the code. Other student create a procedure. So a procedure that contains, say, which was just contain as a parameter, but making all the plots be inside the procedure. So in this case, there was a little higher level of abstraction, because the student create something like a snapshot of the motion, and then he animates this procedure. So, and of course, while he was defining the procedure, he has also to understand the patterns that were involved. So this one was the code more or less behind. So sometimes there are also some other commands which we didn't report all of them in this presentation, which is the main part. So there was just one procedure with the snapshot. You can see at time t the situation is this one, and and then the animation of the procedure was quite a simple exercise for them. There are also some. Now be patient for this this images, because they are quite, say, hypnosis. There are also some cases in which the students really didn't focus correct on the mental strategies. Sometimes it's just in the use of the Maple commands. We train them. Say some of them make really a huge training in the use of Maple, but you can also you learn also every time. Me too. Every time I learn something new about Maple, and sometimes they made some really wrong scaling of the graph. So this one is very little compared to the size of the graph. This is the motion. Could be true. Could be right. Or maybe it's not right, because also the contextualization is very important. So this wheel goes below 0, so it's say if the ground is at 0, it's kind of strange. So this is they didn't apply correct the abstraction and the logical process in this case. So this was just a bunch of solutions that we had a look arising from students. But it's also an important issue to train the teachers on how to use these chances in order to really make a good work with students. yeah, for example, say from the teacher's side, we wanted to train them to understand the processes that are behind these animations. Of course, teachers can enrich their practical and theoretical explanation with the animation. Okay, they are not just nice to see, but really they activate mental processes. And okay, they can also enhance the learning of scientific concepts, which otherwise, say, could be very, very difficult to express, maybe just in the mathematical form. Okay, for example, the trajectory was not that bad anyway, but it was not easy to see what was like from just the mathematical form. With the animation, was like funny and easier to understand. And in order to train the teachers, I go back to one of the projects that we are managing. This is called problem posing and solving. So this is for the teachers. This project was, so it is, because it's still active. It's financed by the Italian Ministry of Education, so it's really a national one. And it's done for improving the didactical of mathematics and in general STEM disciplines. We involved many schools, like more or less 800 schools, more than 1,000 teachers, and a lot of students. These teachers, they have their own online course, let's say, in which their students are subscribed, let's say. But teachers are also connected in a community with other teachers and with us, let's say, which we call ourselves the tutors, because okay, tutoring is quite essential for them. Otherwise, say, they learn a little bit. We made some in-person meeting all over Italy in previous years, but sometimes it's not enough. So the online community is very important. For example, during the year, say usually we have some weekly online tutoring. There are some people dedicated to this, and we had this weekly synchronous tutoring, both in the usage of Maple, but also in other tools, of course. Then teachers collaborate also via a forum. The collaboration with the tutor is quite, let's say, strong, well connected. Since, okay, teachers maybe prepare some files to present to their students, but maybe they ask also our opinion because, okay, we are very good in using Maple, so we can give them a very nice feedback. And of course, the advantage of a community is that you can share your work and get some ideas from other people, also other teachers. Maybe they use I use this file in my classroom. Another teacher say, okay, I can use it too, maybe with some modifications. So it's a very nice community in this sense. And I focus now on two problems that were prepared by teachers. For example, this one, there is a craftsman which needs to design a tile, let's say, a tile which is really a geometric shape, a nice shape. So it starts from this square. Then I want to, let's say, rotate it a little bit. Say I want the student to state what are the main steps to do to create a really nice tile. And okay, in this example, the first step is to really scale a little bit down the square. Then rotate it a little bit, and I get, let's say, that it fits perfectly with the middle point of the sides. Okay, so teachers created this animation, so it's very good. And teachers themselves, because they are in some sense also students for us, they really applied many of the mental strategies we have seen before. Say, for example, here the compositional problem, you have a first shrinking, then a rotation. But then, I didn't say something before, but also the generalization is quite important. For example, okay, I have some example in which I can really go on with creating this style in order to make it really, say, more or less, okay, not till infinite, but let's say something similar. And also try to generalize with other polygons. For example, okay, this one is increasing the number of sides. Okay, and then teachers with the students can really make all the remarks. For example, this is less like while increasing the number of sides, the shape is really getting very close to a circle. So it's like also for calculus, for stuff like that. It's quite nice anyway. And another problem that the teachers created, maybe this one is more standard, but it's anyway in this sense quite nice. So for example, I have this shape of a trapezoid. What happens if I rotate around its, I think it's the major base, but I wrote minor, so it's okay, sorry. Okay, everybody knows here what happens, so, but what about the mental strategies that were behind it? For example, okay, the one is the abstraction, just to move from the planar setting to the space. Okay, after this rotation, we made it on one side, but you can generalize, of course, it. So the teachers created an interactive components in order to vary which segment in the space was the base of the rotation. So okay, this was very easy to do with Maple. And also, say, try to let students insert another plane figure in order to see, say, how differently is the shape of the object in the 3D space. Okay, for example, this one, for example, is another animation in which, okay, there's a hole because I use another segment, another rotation axis, let's say. And okay, the advantage is also because to use this animation, it's since we are using a lot the online environments, we have Moodle platforms, okay, for the community of teachers, but also for students. So this animation are very easy to share, even in say these are GIF files. So it's even in a forum or okay, very easy to share online. And okay, and that's it. This was the last animation. I go straight forward to the conclusion. Okay. In this work, we try to analyze a little bit the computational strategies used in animated graphs, in the creation of animated graph. There are different strategies, both from students, both from teachers. And in some cases, okay, I focused on the main strategies, but really I think that in all these solutions, many more strategies were adopted, just maybe a little bit more hidden. But then in the end, say, as our experience says, students had a lot of fun in working with the animation, so it's kind of say that math is fun too. And okay, and with this approach with teacher, we try to make really these things used in the common teaching activities in high school. And that's it for now. So this is the contacts, and thank you for your attention. And I'm available for question. Yeah.
So do these teachers think more about, I have a practical problem and now I'm going to wedge the theory into it, or do you do that theory?
Okay.
Or do they come up with like, we need to cover this particular concept,
yep,
and now I got to come up with a bunch of
okay.
examples?
Okay, there are different possibilities. Okay, usually, I also prepare some contents because, for example, the one developed by students was really a kind of training for students. They were asked every time a problem, and I was in the creation of these problems from the mathematical point of view too. And I was also usually I was starting from the mathematical element, let's say, and then try to, let's say, to enrich it with some kind of contextualization. So this was my personal approach while I was creating some of this kind of problem, contextualized problem. Probably say maybe it's not always like this because sometimes I was also like watching online something and they say, okay, but this one could be modeled mathematically, and so I applied also I create a mathematical model for that setting. So I think it's not just one of the two strategies. I think that okay, for the didactical purposes, you have to know what you want to teach students for. So what is the mathematical topic, and then maybe create some at least nice context. So maybe getting real data or stuff like that.
So the animated thing at the end where you were rotating around, is you have that like on the cloud or something that
Yeah, okay. Yeah, so all of it are, I think we are online. So I don't. Say the community is quite close. Some of the communities, not all of them, because say if it's a community of high school teacher, we say you have to say enroll to be a high school teacher in order to participate. But there are some other projects which are really completely open. For example. So the one less mathematical, let's say, because the other one were really devoted to a specific kind of user, so that's why they were closed, let's say. But the other one, we prepared also some online courses about really basic mathematics for many disciplines. So these one are open, so everyone can access it. We don't have this approach actually, this problem solving approach. We applied in the project, which was called problem posing and solving. So it's mainly devoted to students
But the revolution that was you used Maple to
Yeah.
do that.
Yeah, of course.
Yeah. Okay.
So do you try to separate the computational thinking from the Maple implementation? So for instance, when the student looks at the ladybug problem, would the student say, oh, I'm thinking of a solution that works like this,
Yeah.
and then find the Maple command that lets them implement that idea? Or do they kind of just stumble around, find a certain command by chance, say, oh, this one works, and then have to adapt their strategy to fit the command? I'm just wondering if there's like
No, okay. Usually we give the students the problem, and then they are free to use. Okay, we ask them in this case to use Maple as in order to, let's say, really, because it's a very nice tool, as I said before. So we ask them to really use the software. So no other tools. But anywhere they were left free. You say they could use anything. So even if it was static, a static solution, maybe it could be really good anyway. But say we focus really for this mental strategies. We focused on animation because really we think that they give a little bit more than the usual, let's say, for really computational strategies and stuff like that.
I know I've worked with people who have done this kind of thing, with high school students, just as introductions, basically to computing, and animation and visualization. And I think it demystifies so much of what those pictures when you see how you construct them, element by element, or whether you do the composite frame when you animate that, or whether you put all the different animations together. Just that decomposition of the problem into what the elements of it are translates into uncountable situations and has benefits, broader impacts long beyond the pretty pictures.
Of course.
Or the silly pictures that we make.
Yeah, of course.
And I think that's I think it also the demystifies Maple in that sense too, and that okay, that's just an arc, that's just a line segment, and if I put things I can, if you don't think about the whole thing, if you think about starting small, doing one part of it, that's all your computational thinking, right?
Yeah.
I think that lets you think in how to use Maple too. I agree. You don't start by doing all the fanciest stuff.
Yeah. So really, these strategies are say founded by mathematics, let's say, mathematics and computer science, but really they could be adopted in many different settings. So that's why I was glad to be here. So in order to really get also some other experience by other people that are really teaching or with Maple or with other tools, I don't know, I say anyway. mathematics or STEM disciplines or other things, in order really to share the ideas, share the possibilities, share everything, and that's it. Yeah.
So when you're introducing this stuff to high school teachers who maybe haven't done anything like this before, are they then taking it into their own classrooms? Are they actually adopting some of this, or
Yeah.
some of them adopting
Yeah.
this, or?
Okay, some of them are really daily adopting these strategies. So the best teachers really, they're applying it a lot. Okay, of course the situation is quite general when you face more than 1,000 teachers. You have some that are very good, some of them they are not so good. But I think that most of them has applied these strategies at least once or twice in a year. I don't know. Let's say I'm just trying to give you an idea. Say, okay, the situation is quite large when you have so large numbers. So, but really, I can assure you that some teachers use it a lot in their classroom. So, for example, as I remember, there were some students they were getting their diploma. So they were finishing high school. There was the exam. And they prepare. In Italy, you have to prepare a little presentation of a topic, let's say. And some students presented some problems. I don't know exactly what, but using Maple, using animation and stuff like that. It was very very nice to know. Yeah. Okay, I think that's it. Thank you again.